What I want to tell you about is some things I've been doing in the last 2-3 years maybe that have all the perspective of looking at how you can develop complex microstructure in soft amorphous materials, and how actually this the specific feature of the microstructure actually have an effect on the mechanical properties of these systems. So you can think in this sense to my title of soft matter in construction. So you have a soft material that is developing from a liquid into an amorphous solid, and I would like to understand how I can control the this development in a way to design maybe the mechanical properties of this amorphous solid. Or you can think about it as applied even to really construction materials, because as you see I am working in a civil engineering department, and I will say in the last part something about that. Okay, so that's the outline of my talk. As I said, I will start from a case that I think it's very typical of soft matter system. That is the case of colloidal gels that forms in a suspension of colloidal particles, and where I will try to say how you can link actually the microstructure, the study of the microstructure, to the development of the mechanical properties of the amorphous solid. And then I will show you also something that we've been doing on the same type of problems when it's related to a formation of a complex interface that can be used for developing novel concepts for nanocomposites. And finally, I want to go really into construction materials, so I will tell you something about what we've been doing or try to do for hydration of cement. Okay, so as I said, let's start from a case that it's very typical of soft materials in terms of soft matter. So you have a suspension of the colloidal particles, and typically what happens is that in experiments you can control the strength of the attraction very well between the particles, so you have particles that can stick together, and the volume fraction, the solid volume fraction, so the amount of particles that you put in the solution. And in fact you realize that playing with this controls parameter, but actually also playing with the processing condition, you can actually get a number of very different microstructures, going from very fractal thin gels up to dense porous solids and very fairly homogeneous amorphous solids and glasses. And the variety, the diversity of this structure is amazing. But I found even more interesting that in fact this can become a way to really design mechanical properties that can be unusual and not trivial to obtain, and interesting for a number of technological applications. Let me give you a couple of examples. This is actually a situation. So if you take a very dense suspension of sticky particles, what you can have is that particles, they will stick together and form kind of clusters, and then these clusters will actually assemble into a dense glass. Okay, and what we have done, for example, is to look at the elastic properties of this type of dense sticky solid, and you realize actually that the contribution, the elasticity of this material is actually dominated by the weak contribution between these aggregates. So this red line is the theoretical prediction based on a simple model for computing the contribution to the elasticity that comes from the inter-aggregates connection. And these symbols are experiments performed on different colloidal suspension, dense colloidal suspension. This is the elastic modulus, the shear modulus as function of the strength of the particle attraction, and this dashed line up here is actually what you would get from as the contribution to the elasticity from the particle-particle interaction. So the fact that you have these aggregates and then these aggregates form the solid can actually change the elastic response of the material quite a lot. And so you could think of inducing this type of microstructure to actually change in the same material its linear behavior, its elastic response. This other example, it's taken from lysozyme, which is actually, so in a protein solution, the strong attraction between the proteins can actually produce a complicated structure like that is a bicontinuous gel network due to an arrested spinodal decomposition that is taking place. And in fact, the experiments have shown a very nice set of experiments have shown that when you deform this system, you can get two separated, very well separated, distinct elastic moduli, one that you can detect on short time, and then a distinct elastic modulus that you can detect at longer times. And so with the simple modeling, we have been able to show that in fact these two distinct moduli, you can directly connect them to the feature of this complicated bicontinuous network, because it can be associated to the stretching and the bending modes of the branches, of the thick branches of the network that can develop over quite different time scales. So this was just, I don't want to go into details of this, but this is just a motivation to show that really you can think of inducing a specific type of microstructure to bring in some interesting mechanical properties that were not there at the beginning. And if one wants to push it further, an interesting thing is that you can now think of designing, for example, a gel network, so where under deformation you break up part of the gel, but in fact, as you proceed shearing the system, you also bring part of the structure together. And so if you were able to properly design this feature, in fact, you could design a system in which you break the structure so the system starts to flow, but then the same structure actually self-heal. And so it arrests the flow and so on. So these are properties that are actually, this is what people are really trying to do in the last few years in experiments. And but it's clear that if you want to do it, if you want really to design it in the right way, you need to control you really need to control very carefully how, first of all, how things break in this type of complicated structures, and second, to rationalize how breaking in different parts of the structure actually can have effects on the reorganization of the structure itself. So this is the question that I would like to address now, and I will tell you how we did it. So what we did is that we designed a simple model for this type of gel network that can give you a structure like this. It's a particle model, so we have colloidal particles that can stick together and form, stabilize this type of, well, it's complicated, but it's relatively simple type of gel network. And that forms, I don't know if you can see in the structure, basically it's a network of chains with that interconnect in nodes. And it's not specifically related to one given colloidal system, but it reproduces a number of generic features of colloidal gel that can form in fairly dilute conditions, so at relatively low volume fraction. So basically what we do is that we have an effective potential between these particles, which consists of an attractive well, which mimics the attractive interaction between the particles, and to this we add an angular local rigidity between bonds that actually helps in stabilizing the type of structure that I told you. And in fact, that this type of simple colloidal structure do have a local angular rigidity, has been measured in experiments in various ways. And for example, also the fact itself that you form this colloidal network at relatively low volume fraction, which have a typically local coordination number that it's fairly low, it's between 3 and 4, does support the idea that you do have a small local rigidity that helps stabilizing this type of open gel structure. Okay, so this is what we do is that we implement this type of model in molecular dynamics simulation, and then we look at the spontaneous dynamics of the system under thermal fluctuation, or we can deform the system and look at how deformation actually induces stresses in the structure. So here, this is maybe to have a bit more precise information. This is the structure factor that we can measure in the system in the molecular dynamic simulations. And so you can see that you have, so this is measuring the correlation between pairs, between particle positions. And so you have a peak that corresponds to particles that are nearest neighbors within the attraction well, so the bonds actually between the particles. And then the interesting thing is that you have, this is a wave vector expressed in terms of our unit length in the simulation, which is the particle diameter. So you have an excess of spatial correlation also at smaller wave vector. That is, and this is what basically capture the structure of the network and the presence of long-range correlation that are related to the fact that it's a spanning network of particles. Here we have separated the contribution that comes from all the particles, and this dashed line is the contribution that comes just from the nodes of the network. As I said before, we have this type of network that is basically chains connected by nodes. And so you can see from this curve, that is the structure factor only of the nodes, that basically the nodes of the network are not spatially homogeneously distributed, but you can see features of correlation already also in the nodes of the network. Okay, so starting from this, then you can look at the microscopic dynamics of this type of networks, and this already tells you something interesting, I think. So here this is quantified in terms of the intermediate scattering function. That is what you can measure, for example, with light scattering, and that you can compute in the simulations just from the particle coordinate, and it's basically a way to measure the correlation in the particle displacements over a distance of the order 2 pi over q, where q is the wave vector. Okay, so it tells me how the displacement of one particle actually becomes uncorrelated over a distance of 2 pi over q. And so when I look at this type of function, I do see this is for a wave vector that it's of the order, let's say, of the mesh size of the network. And so there you can see that actually the microscopic dynamics of this type of structure develops some interesting features that are, for example, very similar to what you would observe in a glassy system. So you have this plateau in this function that clearly indicates the presence of a localization process, after which then the relaxation in the particle displacement eventually decay to zero. But also, yes?
Am I to understand this as purely Brownian thermal
this
action? There's no imposed stress or strain?
Here there is no imposed strain. It's not even Brownian actually, because here I'm just, what I'm even showing is just Newtonian dynamics, to be precise. But you can do the same, we have done also the same simulation using Langevin dynamics, for example. And what happens is that this first decay, which is associated, it's really determined by the microscopic dynamics, the type of integrators that we use for the type of equation of motion that we use. It's different, but what I'm going to talk about, which is the last part of this decay, this will not change. Okay, so the decay from the plateau also is a stretched exponential decay in a certain range of wave vectors. And here what we have done is that in the simulations we have also considered the same network once that it's formed, and then we have frozen in the bonds. Okay, so we have taken the same initial network and then frozen in the bonds so that things cannot break. And then this is the relaxation function that you would measure in that case. Okay, so it has this initial decay, which again is dictated by the specific microscopic dynamic that we use, and then finally it stays, it reaches a constant value because the network does not restructure over time. Okay, so I just want to stress that this network it is actually an elastic solid. So if we deform it, we can measure a finite elastic modulus at low shear rates. That it's not significantly dependent on the shear rate. Okay, and in order to quantify also this type of dynamics that develops in the network, one can look at the fluctuations of the average dynamics, so what is usually called the dynamical susceptibility chi4, which is given from the fluctuation around this average dynamics as it is measured by this type of relaxation function. And this as you can see it here, these are these crosses here. As function of time, it develops a peak that again it's very typical of glassy type of dynamics, and it grows. It's a peak that locates around more or less a time scale that it's typical of the relaxation time of the network over this length scale Q equal 1. And this fluctuation, they actually measure the enhancement of correlation in the particle displacement due to the fact that in fact the dynamics is cooperative, and this is what produces this type of complex decay of the relaxation function. The interesting thing here is that if we compare this function with the one that we measure in the frozen network, which is this dashed line here, one can see that the signal of this cooperativity, as it is captured by this function, is actually much basically negligible in the constrained network, and instead becomes significantly significant in the restructuring network. So this tells us that the restructuring of the network actually is happening in a cooperative way, and this is what is probably interesting also if one thinks of the problem I was mentioning before. So when I start to break this structure, how the network will actually reorganize. So the idea was that one needs to understand this thing about the microscopic dynamics in order to get a picture of how the system will behave from the mechanical point of view.
Can I just ask a question? So in the early time dynamics, it's basically the molecules are attracted to each other and they form these ribbons, form the structure.
Now, actually, here the dynamics is measured once the network is already formed. So
the entire thing is once.
Here, basically, the network it's overall staying there. It can restructure here and there, but it's persistent. That's why if we shear the system, we do observe an elastic modulus. Okay, and this dynamics is I start from the configuration once that the network is there and it's is stable. Okay, I mean in the sense that it's there and I don't see significant variation in the structure, and then I look at how the fact that actually the network once in a while there is a bonded break, how this is an effect on the correlation in the particle displacement.
So you're putting some randomness into each of the particles?
It's just thermal motion.
Just thermal motion.
Yes.
You said that there are elasticity properties. This is on known timescales, or is it just viscoelastic at initial time state before it starts to restructure?
Actually, we do see an elastic response using shear rates, which are so we deform the system at fixed shear rate, right? And then you measure a modulus, okay, and you can and this modulus does not significantly change in a relatively wide range of shear rates, which are of the order of the relaxation time of the system. So yes, yes, this is. But I can take this shear modulus and plot. Or I can take the stress and plot it as function of the deformation and get a shear modulus. Okay, so in fact, having seen this type of scenario for the microscopic dynamics, our idea was try to, okay, how can I really connect it to specific feature of the structure of the gel? right? So the fact that this type of networks and systems have a microscopic glassy dynamics has been observed in many systems, and a lot of times, nearly basically always in experiments. And what we can maybe try to look in simulation, that in experiment it's not so easy, is really try to figure out which features of the structure, and in particular in this case, which features of the restructuring process produce this type of behavior. And so what we have done is an analysis of the microscopic dynamics that allows you to map into real space and into the real space structure of the network what is going on. So, and we used a method that has been introduced some years ago by Peter Harrowell and his collaborator for investigating dynamical heterogeneities in glassy systems. And so what you do is that you take an initial configuration of the system, and then you take the same particle configuration but with different velocity distributions that have been extracted from the same Maxwell-Boltzmann around the same temperature. So you have all these copies of your system, these blue ones, and then you can let each of these copies evolve over time, and then you fix an interesting time scale that it's relevant for whatever you want to study. And you analyze the dynamical properties at this time over this sample that you have generated in this way. And by doing this, you can actually look at the distribution of each particle displacement over this sample. So because the particle configuration is exactly the same from the position configuration, it's the velocities that have been change across this sample. So then I get a spatial distribution of displacement, for example, and I can try to map back this into the information, like this initial particle that was in this specific part of the structure. Is it likely to move more or less after a certain time? So I get a spatial distribution of how the dynamic is actually heterogeneous in the system, and I can try to connect this with what I know about the structure. Okay, so this method has been, as I said, was originally developed for dense glassy, for looking at supercooled liquids. So a system in which you have glassy dynamics, but the system is very dense and homogeneous, and things are moving nothing is moving basically. In this case, we have extended this type of analysis to this type of dilute gels, where in fact everything is moving a lot. So it's not so easy to obtain the final information. So what we did is that we used this study that we had of the frozen network at the network with the frozen bonds to actually subtract everything that comes just from the network vibration. Okay, so what we are left is the displacements. So we have a map of displacements that are actually corresponding to the structural relaxation of the system, the final overall relaxation of the network, and not just filtered out of the network fluctuations. Okay, so what you get is this. No, first of all, let me, so we have started from this type of physical picture of the network, and by doing this type of analysis, you transform your physical picture of the network into something like that. So here what we have analyzed is in fact not even a dynamical information, but it's just the local density of nodes in the network. So what it means is that we take a particle. Here I use this bonds representation just because it's easier to see things. And the color code is this local density of nodes that I was talking about. So I take a particle and I look at how many highly coordinated particles are around within a certain distance. So this is not the local coordination number of one particle, but it's really how densely connected is the environment around that particle. Okay, and so I am showing you first this type of spatial representation of the network, because you can see that it's very heterogeneous. So there are regions which are highly connected and regions like the blue ones which are very poorly connected.
What's the nature of the order parameter? This descriptor you have of averaging, do you have an order parameter representation of that?
Not really, I'm not sure.
I'm just trying to understand the localization, why you're drawing this structure in terms of fibers.
Because if you want, it's just the particle distance, right? So I have started from this picture of the network here. So this is the network of particles, and so I can just define the bonds in terms of the particle distance, which is just basically set by the interparticle potential, the attractive well.
Fibers, can you link one of those fibers to this picture?
This is exactly the same picture. It's just that I am representing one bond between two particles as a stick instead of showing you the two particles. This is what I'm doing.
So a stick appears whenever they're bonded?
Yes, sorry.
But then you've got the density of the stick. So
the color code is the density of the nodes around in the environment around that specific bond.
Right, but I mean, I think isn't that trying to identify an order parameter? I mean, that you could view these molecular dynamics simulations as trying to do that.
Yes, I think so. And maybe there will be some development in work.
So this figure, if you like. Yes, so in some sense this is illustrating the extent to which this is a glassy system. I mean, is there a glassy signature when you look at this?
Yes, but maybe in a not so straightforward way, as you will see in the next thing. Let me. So this tells you something in this direction, but at the level of the organization of the structure. Okay, so let's see which consequences this has on the microscopic dynamics. This is what I want to say. Okay. It is a percolated network. This is an information that also maybe, so basically all the particles belong to the network. So from this point of view, it's, the whole thing is connected more or less. And here I am trying to distinguish between parts that are more tightly connected because there are multiple paths connecting them, and parts which are poorly connected because I think this is going to have an effect on a role in the dynamics. So now I'm going to, what we have done is that by doing this isoconfigurational ensemble analysis that I was explaining before, what we have done, having fixed, so I have my copies of my system, right, with the same particle configuration and different initial velocities, and then I evolve each of these particles just with molecular dynamics. Then I take a characteristic time that in my case it's where I think once I saw this peak in the cooperativity, I want to look at that time scale, right? This is the time scale that it's interesting for the reorganization of the network, where things interesting at that level happen. And I look at spatial distribution of dynamical quantities over this sample, okay? And in particular, one thing that I looked at is where things have broken. Okay, because I want to try to understand where it's more likely in this type of structure to break things. Okay, if there is something that I can learn from the spatial distribution of breaking events. So I get a map like this. So now my picture of the network is changing into something different. Here I am using the same color code, but I have introduced another thing that is the thickness of these fibers, and the thickness is proportional to the likelihood that a breaking event will happen. Okay.
The thicker, the more likely, the less
yes,
likely.
the thicker, the more it's prone to break when I look at this thing. And so one thing that you can see, I hope, because maybe the colors are not so nice, but you can see that red things tend to be thicker. So this tells me that it seems that the network tends to break where in the regions where it's more densely connected. So these regions which are more densely connected, which are also probably, I mean, the parts that are most important for getting the mechanical stability. On the other hand, they seem to be also the regions where things tend to break more likely. And in fact, we can, yes?
Sorry, is that the number of bonds which will, the number of breaking events per bond, or the number? I'm worried that
it's
things
not
break more there because there are more bonds there to start with.
it's per bond. It's per bond. So it's not.
So is it that things break more in the red regions because there are more there to start with?
There are more.
There are more bonds in the red regions to start with.
No.
So they're more likely to break.
No, it's just it is independent from the number of bonds that are there. That is just the break
It's a breaking probability per bond.
it's the breaking probability.
The question still needs to be answered.
Well, one thing that you can see is that in fact, if you compute stresses, for example, local stresses in the structure, you can see that these regions are the regions where tensile stresses tend to concentrate. And yes, I agree, sorry, this is related to the fact that you have more bonds, and so you have this environment is under stress more than the other environments. So, but what I wanted to say is just that it's not that I'm just counting more breaking events because there are more bonds. So this is what you get, and then the other thing that then you can say is that okay, once that I have these breaking events that happened in these thick parts, where can I see the consequences? So I have that in my network. Once that I have filtered all this vibration, I have that the restructuring of the network happens via this bond breaking. And then the effect of the restructuring is that I break something and then particle can move, right? So I can identify where are the, once that I break one thing, where are the major restructuring process in terms of particle displacement taking place, okay? And so then if I use the thickness of the fibers to represent this feature, right? I get this other picture of my network. So you can see that you break the things more likely in the red parts, and the consequences of this in terms of particle that displace because of this breaking event actually takes place more in this blue region. So you have these blue sausages going around in the network. Okay.
Do these blue regions terminate with these red zones? I mean, they start at one and end at another?
Yes. So because these are the blue regions, these are the poorly connected regions. So these are mainly chains, or with the fewer attached to fewer nodes. And so on one hand, one say, okay, this is what I would have expected, because in fact it's clear that there things are more free to move. Okay. On the other hand, what is interesting is that this tells you that the consequences of one single bond breaking actually can propagate far away in the network.
So,
and yeah.
So it doesn't mean that there are other bonds breaking there. It means that you've got wiggling and flopping occurring
Yes.
in that region. So
Yes.
it breaks here, then it flops over there.
Yes,
Right.
it's, this is the idea.
But in this change, do two particles come into contact?
Yeah, they can break
And
and
so
they can
that-
reform.
So there's a paper a few years ago by Ajdawi and Picard called
Yeah.
The Elastic Consequences of a Single Plastic Event. And what they did there was consider a tiny localized rupture and then how that propagated elastically, but that was simply due to the Osine tensor.
Yeah.
And I've always wondered, I mean, do you recover that on a large enough length scale? Because presumably on a small enough length scale it's very highly heterogeneous and you wouldn't just apply this continuum
Yeah, so I
to it. So
I think that this is what we would like to do, but you need to go to a very large
Very big
system in order to
right.
see if you
Can you get a
recover
bigger
that.
system in your simulation to do that? Or is that
Yes,
just
yes,
impossible?
yes. I think, of course, you would not do it for an enormous system for from scratch from the beginning. But once that you have identified which are the interesting things to look at, yes, you can do that. And the thing is that, for example, one thing that we have done is that you can deform the system and then take it back and look at which part have rearranged in a non-affine way. And so what you see is that non-affine displacement tend to happen in these blue regions. Right? So these poorly connected regions are also the regions that are probably containing most of the non-affine displacement under deformation. So it's suggesting that there is a connection between this type of setup of the microscopic dynamics and its cooperativity also for the deformation of the system. And then you can think that this is the type of microscopic information that you can try to put into a constitutive model and to see what happens. This is was basically one of the motivation. Yes.
If one breaks in the red region, how long does it take to be recaptured or form another bond versus the blue region? I mean, there are more particles around, so it could just stick somewhere else and start.
Yes, yes. So it does happen like that, and we have done a survey of these rates of reforming bonds, etc. But in this moment, I cannot tell you exactly.
Presumably there are more bonds hanging around,
yeah.
But they're also bonded with more friends, right? Because it's so there may not be so many free sites to find each other.
So this is the thing that
that brings me to another question. Is the number of bonds per particle limited?
No, it's not limited. I mean, but it is somehow limited because the rigidity that we impose. So you cannot, let's say, bonds in which you would tend to form angles that are smaller than will they will be very unlikely because you would have to pay a lot of price in energy. This is the thing. So there is this mechanism that all the parts of the structure around, they are not necessarily so ready to take up other bonds. And in fact, we do see that in this model, basically, the number, for example, once that the network is formed, the average number of the average fraction of particle with a certain coordination number does not change significantly, although there is a very slow aging.
What is the average strand length roughly? I mean, so you have to.
It's the strand length. Okay, we have a distribution of length which is actually exponential, and it is around 5-6 particles.
That was the peak you showed us earlier.
Yeah. Okay, so this is. So I think that this tells you what one can try to do, or what we are trying to do to say, okay, I form this type of complex structure, and then by doing this type of studies of a space-resolved analysis of the microscopic dynamics, I want to try to really be able to say, how can I design the microstructure to have certain type of microscopic cooperative processes that can be interesting for the development of the mechanics. And as I said, I'm very late, so I won't be able to tell you nothing of what I planned. Okay, but let me try to go to the next things and tell you how you can use this idea actually to look into a different problem, that is the problem of formation of a complex interface. So we have used this type of philosophy, although not developed exactly in the same way. But the idea is again that you want to look at how a relatively complex microstructure develops, and how this and have hints on which features of this process development and of the microstructure actually will affect the mechanics. This is in a different problem. The problem we are looking at now is the formation, the absorption of nanoparticles at a liquid-liquid interface. This has been motivated by experiments done in the same institution but in the material science department, where they actually assemble nanoparticles at oil-water interfaces, and the idea is that if you can control this process, you can actually induce a pattern on these interfaces that then can be transferred to templated and used for several type of applications for sensors and so on. So the idea is that you have this they have this droplet of oil in water or water in oil, and in this case it's water in oil, and they inject the nanoparticle in the droplet, and the nanoparticle, they basically go to the interface because of the free energy gain in removing part of the interface between the two liquids. And the interesting thing is that in fact in the experiments what they do is that they monitor the shape of the droplet. With this experiment it's usually called the pendant drop tensiometry, and from the shape of the droplets they actually can how it changes as the nanoparticles go to the interface. So they can use Laplace-Young equation to calculate an effective surface tension. So this is the interface tension of the system that it's progressively covered by the nanoparticles, and so it's decreasing over time. And they monitor this decrease of this interface tension over time by they want to connect this decrease over time of the interface tension to the adsorption process, and it becomes a way to monitor the adsorption process.
This is done with a feedback to change the pressure to keep the volume fixed?
Yes. So, okay, so one thing that they saw is that in fact if you increase, so at the beginning if you increase the concentration of nanoparticle in the droplet, you start to go from a situation in which the interface tension goes down and then it seems to reach a plateau which would correspond, let's say, to the maximum coverage of the droplet, to a situation in which you start to see something a bit different, because it decreases, it seems to reach a plateau value, but then it starts again. So this gives you the idea that at some point you start to adsorb the nanoparticle, but as the adsorption proceeds, there is probably something else that is going on, and then this interferes with the adsorption process, and something else comes from the microstructure of the let's say the cooperative or collective dynamics that the nanoparticle starts to develop at the interface. So we wanted to look at this and to try to figure out what are the mechanisms controlling this type of behavior. So what we have done is a combination of a grand canonical Monte Carlo with the molecular dynamics simulation. So the idea is that we have a grand canonical Monte Carlo that we use to mimic the adsorption process, where the chemical potential here is the adsorption energy of the particle. So it's the free energy gain for a particle to go to the interface, and this is proportional to the particle size. And then we combine this with molecular dynamics, because in fact this gives us the possibility to monitor how the development of the organization of the nanoparticle at the interface and their microscopic dynamics as you keep adding particles. Okay, and so we have what we actually do is a molecular dynamics simulation over which we have these Monte Carlo events, and we can change the rate of the Monte Carlo events over the molecular simulation time to use this as a parameter, that is the rate at which the particle will come, assuming that if you have a higher concentration of nanoparticle in the droplet, you will have a higher rate of nanoparticle coming at the interface. Okay, so we have a parameter that we can play with, that in the experiment it's basically fixed by the chemistry, so they cannot change it, and we can test how things depend on this fact. So the nice thing in this type of simple schematization is that actually you can put a lot of ingredients. You can use a simple model, but put a lot of ingredients that come from the experiments. For example, in this case, we know that the droplet is a millimeter size and the particles are nanometers, so we can just use it's fair to use just a flat simulation box. We have let's say the size distribution of nanoparticles that are available in the bulk, and so we can use that for the simulation. We model the particle just as soft disks basically on this flat interface.
These
Okay.
nanoparticles have any kind of ligands, any kind of
Yeah, so the
decoration?
nanoparticles, these are oxide core nanoparticles covered with the PEG that is grafted on the surface. And okay, there are several indications that basically this is they don't attach to each other at the interface, and it's just a soft repulsion. And this was just the first step in this model system, because then the idea is that then you can functionalize the PEG and then get things that can stick together or can cross-link and do more complicated things. Okay, so what you get in the simulation is that then you can compute 1 minus the surface coverage, that it's basically related to the interface tension that they measure in the experiment, and how this evolves over time. And okay, here in the interest of time, I'll just go shortly. What we have figured out, we have analyzed in the simulation what is the role, for example, of the attraction strength. What is the role of the distribution of particle sizes in this process in which you keep adding this nanoparticle with a certain weight. And for example, you can recognize that clearly what happens you can use the absorption energies that are typical of the experimental system that we are looking at, and so you can recognize that this corresponds clearly to an out of equilibrium absorption, where basically everything is absorbed and you don't see hardly anything desorbed. And you can see that in the simulation you do develop the same type of feature that you have seen in the experiment. So if we look at this, and this happens for high enough absorption rate. So at low absorption rate, this feature eventually goes away. But if you do the absorption sufficiently fast, as you would think that would happen when you have a lot of nanoparticles in the droplet, then you see the emergence of this feature. And if you consider a monodisperse system in the simulation, you can actually recognize that what happens is that this fast absorption basically produces a jumped interface. All the particles, they immediately go in the interface and they form a supercooled, disordered interface at a density that is actually beyond the one that you would need to get crystallization. And then you can, in fact, you can look at the bond orientational order of the particles at the interface, and you can recognize that, in fact, what happens once that you enter this plateau is that the particles, they actually start to order. So when you are at this stage, basically the interface is jumped. There is no space for absorption. Absorption becomes much slower, and at the same time the interface starts to order. And while ordering, you form these ordered domains with defects in the boundaries, and in these defects is where actually the absorption can start again, where you have locally things that can actually form. So this is, for example, the probability of the bond orientational order value in the region. So the red one, the green one is the one for over the whole system, and the blue one is the one around particles that are newly absorbed in this when I get out of the plateau. And so you can see that the particles that are absorbed there, they are actually absorbed in regions where the local bond orientational order is lower. So these are the defects region. And so this is interesting because it tells you that in fact you could use this kinetic, you could control the kinetics to actually control the type of defects that you have at the interface and the amount of them and how they would evolve, because then this final part is of course controlled by the annihilation of the defects that you get at the interface. So I think that I consumed all my time. No, but maybe I can, if I have...
You started a little late, so
okay.
you've got 5 minutes.
Perfect. Okay, so in fact, this is, I will just to try to be short and to tell you maybe only why one should use this type of pictures and methods and ideas to look at something like cement. Okay. Okay, so what is cement? Cement is the main binding agent of the concrete. And concrete is basically just the cheapest, the most durable the most used building materials. And the production of concrete is enormous. And this is in spite of the fact something like 5 to 8% of man-made CO2 come from making cement. Okay, because cement is basically this powder that then is dissolved in water and mixed with sand and rocks to make concrete. And this very reactive powder is actually obtained by burning calcium carbonate of several minerals, and that's where the CO2 production inexorably comes. So what happens when you mix this powder with water is that the grains immediately start to dissolve and produce a number of hydration products over the times, and with a series of coupled chemical reactions. So it's fairly complicated what goes on. The main interesting, the most probably, okay, maybe I'm a bit biased, but but it's objectively true that the most important of these hydration products is what is called CSH in the cement jargon, that is calcium silicate hydrate. Because this calcium silicate hydrate is actually a very sticky gel that develops during cement hydration and setting. So I think that in most cases people tend to think that drying of cement is drying, but in fact it's not drying. It's this hydration process that actually takes water and put it into this hydrogel that develops over several hundreds of nanometers, and it's a disordered structure and that is very, very sticky, that eventually solidifies into a glue that glue together the different parts of concrete. So it's extremely fascinating for a soft matter scientist to think that this very hard material that you use to make bridges, in fact, most of its strength certainly, but also a lot of other mechanical properties depend on this initially soft nanoscale disordered gel. And the thing is that it's this material, so the CSH, has been, of course, intensively investigated, let's say over the last 100 years probably, but there is, because of the complexity of the material, because engineers, they are of course more focused on the macro scale, there is still very little understanding on the basic mechanism that control the hydration and the development of the properties of the gel, in spite of the fact that at the end the properties of the gel are what you want to control. And okay, just to have an idea of what are the other implications apart of the strength, for example, one thing is that concrete actually creeps. Of course, it's a creep that it's very, very small with respect to polymers or any other system that Susan was talking about. So here, these are experiments done on concrete actually, and this is the creep compliance rate. Okay, so it's very small, but the question is that the point is that this is non-zero, and when you think that you want to use the material for a few decades and you want to build a very large-scale structure, then these are effects that you care about. And in fact, another interesting thing is that it's been suggested that it's been proven by a set of experiments that, to some extent, that this creep is probably associated to the aging of the gel, of the nanoscale gel, over time. And so that's another reason why you would like really to understand how the gel forms. But the main point why there is a lot of interest at the moment in this is because, in fact, because of this CO2 footprint of the material, there is a strong pressure to reduce it. And the forefront of the research at the moment is in trying to devise a new green formulation that would allow to produce cement without such an enormous CO2 fuel production. And so this has moved, again, the attention towards the early stages of the material when it's still a soft material and when the properties of the gel develop. And although you have already some ideas of how to change the chemistry and reduce the amount of calcium that is basically needed there is still a very, the problem is still that when you do this new formulation, you don't get the mechanics at the same level that you had before, and this is because a number of features of the gel actually changes, and so its mechanical property changes. I just want to get where I tell you what is the particular perspective that we use in this type of very complex problem. It's a very complicated problem. One interesting thing is that, in fact, you can follow the hydration reaction, which is exothermic, so you can monitor the heat flow released during the reaction. And so you have this hallmark that is given by the acceleration and deceleration period that in the kinetic of the hydration. And what is interesting is that, in fact, it's clear that these features are coupled to changes of the morphology of the gel. This is the development of the mechanical properties. So you can see that there is an evolution of the strength of the material that is actually coupled to, so the physical properties of the material are coupled indeed to the different steps of this kinetics, and so it's clear that the problem is more complicated than what you would think, and then you need to understand this interplay between the evolution of the chemistry and the evolution of the physical properties. So from this such a intimate interplay between the physical and the chemical properties of the system, I think that is suggestive of what happens in some biological systems when the two things are so intimately related. Okay, so I will, there are a number of questions. I'm trying to select which things I can
We're in a discussion period.
Yes.
Now, so.
Okay. So there is one of the, let me summarize it like that. One of the things that has been debated a lot over the years is what is the structure of this gel and how it develops and how it grows, because these are the things that you would like to control. And because most of the experiments have been done actually at the end of this hydration process, then it's extremely difficult to figure out what leads you there. So it is clearly, there is some traces of for example, from neutron scattering, small angular neutron scattering, you can see that there is a typical building block of this disordered structure, and so people have proposed that, okay, it seems to be seen also in AFM images. It is the idea, what is clear is that this calcium silicate hydrate is actually organized into a complex structure in which you have layers of calcium and silicates that are interlaid with water, and then these form this type of colloidal units, let's call it like that, and then these units, which are typically 5 to 10 nanometers, they organize into this more disordered structure. So people have come up, for example, with a picture in which you have a colloidal gel that is actually produced by sticking these particles together in the simplest probably organization that you would think for a colloidal system, that is a type of fractal gel. Although this is not very compatible with the fact that then the system densifies enormously, so you cannot see any trace of this densification. And also what is difficult is to connect the features of this picture, let's say, to this kinetic, to this hallmark of the kinetic of the vibration. A model that has been an alternative picture is in fact based on the idea that during precipitation you form elongated structures, which are ribbons or sheets, and then this branch due to the defects that are produced during precipitation, and then this branching of this elongated structure is what produces the mesoscale disordered organization of the gel. And in fact, this model, I mean, it's really just a picture. It's never been quantitatively tested, and but you can trace a number of characteristics of this type of picture in the images and in other.
Are those the result of computation, or are they the result of an experiment?
This is images from experiments.
Thank you.
Okay, it's a TEM. And this is the model, right? It's just this sketch, and then you can. So I will skip with the other information I wanted to give you. You can ask me what's the origin of this cohesion between this part where they stick together. But just let me tell you to finish how we treat the problem. The idea is that in fact you have again an interesting soft microstructure that is actually developing in very special out of equilibrium conditions, which is basically the evolving chemistry that makes the hydrates precipitate in the pore solution. So you have the solution, the capillary solution between in the pores between the grains, and there the grains dissolves and release progressively these hydrates that stick together to form the gel. So you have a gel that develops in these conditions. And so what we did is that we used a bit the idea of the assembly of the interface by saying, okay, again I have the formation of a microstructure where the particles are actually coming over and over. It's just that now this chemical potential that I have here is in the non-canonical part of my representation of the process. It's basically related to the free energy gain for a hydrate to be produced. So it's set up by the chemical environment of the system. And we just use it as a parameter that in the simulations we can control to investigate how the gel develops and how these parameters, so how much the fact that hydrates are produced faster or slower affects the development of the gel. And we use effective interactions that are actually consistent with what people measure in the experiments. And we are able to actually, we can monitor the densification of the gel as particles precipitate and start to form the gel. We can actually reproduce this acceleration and deceleration that is seen in the experiments. We can try to compare several aspects of the gelation in the experiments, and we do see that the gel actually forms via nucleation of this elongated structure that then branch due to the presence of defects, and we think that this is consistent with the number of interesting parts. So because I've been so bad with time, I'm really sorry. In case you are interested to know more about cement, there is actually a soft matter web team issue that will come out on the connection between cement and soft matter that will come out hopefully soon. Okay.
A couple of questions, and then we'll have maybe a short break before our discussion.
I was interested in the undercooled system.
Mm-hmm.
So could you go back to that?
The nanoparticles at the interface.
Yes, I was interested in the mechanisms and means by which you can control the rate of undercooling.
Mm-hmm.
Because you described that at some stage you'll have organization which occurs.
Mm-hmm.
So you're quenching below
Mm-hmm.
the critical point.
Mm-hmm.
And
So
then,
this
you're
is
looking at the nucleation and growth stage. So the reason for mentioning it is that in cosmology,
Mm-hmm.
they have a problem of this type, which they
Mhm.
call the structure formation of the universe.
Mm-hmm.
So the Kibble Zürich mechanism
Mm-hmm.
is a programmed cooling, which one sort of imagines the universe went through. And so they basically examine questions of this type in that context, to look at the structure formation as a function of the control parameter, how quickly you go through the critical point. So that looks like a great model system to explore that.
I would suggest this to the experimentally. I'm sure they haven't thought of this application. Yeah, no, I think, but okay, there are probably many systems in which...
It's a genetic mechanism.
It's a mechanism to form glasses, right? So then probably you can find a number of experimental situations that could be good to look at this problem. Here it's a well-controlled system and a well-controlled experiment, and so you can, in this case, you can tune the rate by in terms of the concentration of particles that you put in the droplet, for example.
Other questions? Actually, in this picture, is the color coding the density of the particles, or are there multiple layers?
It's the value of the bond orientational order.
Ah, okay.
So the red, homogeneous red part are the fully
crystallized.
crystallized.
Yeah, okay.
While actually it's exotic.
Okay, good. Yes.
So if I understood this right, then you said that you can relate that your surface tension actually becomes a function of the number of nanoparticles on the interface. But at least for very dense packings or jammed things, I don't think that this is a quite good description, because I mean there are this phenomena that you have, like that you can stabilize non-spherical droplets with nanoparticles on it, and have this Pickering enlargements or bitrials, whatever. So if it would be just an effect of a reduced surface tension, then you wouldn't have them. So here I think, at least for the jammed case, it's much more the elastic properties which come from the jamming, which
yeah, I think you're right. Okay, on one hand, in fact, I think that it's also interesting because from the simulation point of view, this tells you that this rate and then the progression of the decrease of what you measure in the shape is actually a lot related to the fact that you develop these defects, and you can imagine that these defects actually control exactly the elastic properties of the interface, for example, buckling or something. I think one thing that we are trying to do is to do actually a lattice-Boltzmann simulation in which you have the lattice-Boltzmann for the two fluid, and then you have the colloidal particles at the interface, and like that we have a 3D thing in which we can, for example, look at this type of thing.
Good, let's thank Emanuela.